Hello again. In the previous lecture, we discussed the Navier-Stokes equation, which is a balance equation for the linear momentum. So today what I will do is I'm going to discuss the energy equation and it's the simplifications that we will have in applying it to material processing. So as you recall, in looking at the Navier-Stokes equation, we have developed equation 349 down here, this equation, in which we have the rho times the material derivative of the velocity vector would be equal to the sum of three forces. First is minus the gradient of the pressure because it's an opposing force. Second is the viscosity force, mu times the Laplacian of the velocity. And the third one is any body force that might exist in the fluid, such as body force due to magnetohydrodynamic effects or electrical effects or any other effects. The equation 349 is in vector form, and you'll see that the original form of equation 349 is an index notation, is given up here, where we have on the left-hand side, what you see is the material derivative of the velocity vector, and on the right-hand side you have the B sub I, which is a component I of the body force, and dP by dxj is the gradient of the pressure in the of the I direction, and then this last term here is the divergence of the gradient, which is basically the Laplacian if the viscosity mu is constant. So we're going to start from here, and what we'll do is we're going to look at the total energy conservation, and since we're going to study thermal effects in fluids and solids such as casting, then what we will do is we will have to find the mechanical energy part by making a dot product of equation 349 with the velocity vector, because that will be kind of the forces, mechanical forces in the system, and then we'll subtract that from the total energy obtained by applying the first law of thermodynamics, and the difference is going to give us the equation for thermal energy that we would require in the modeling. So if we look here to the conservation of energy, then we see that we're going to now multiply 347, which is this one, by the velocity component VI, and then we will do a summation over the indices, the repeated indices. And obviously we are integrating over the entire volume omega. So term by term, the first term is multiplying by the velocity. Second term is also here, VI would be dxj by d by dxj of VI squared. And then on the left hand side we have the BI now is multiplied by the velocity vector, and then we would have to replace the term in this brown bracket here by its original form, which is the divergence of the stress tensor itself. So if you look here, this equation 344 gives us the divergence of the stress tensor, and when we obtain the divergence of the stress tensor, we will be able to write it down here in equation 350, and that is in the last term. So that would represent kind of the mechanical work in the system. And if you look at the mechanical work, we have here terms that are all integrated over the volume. Then what we could do is we would use Gauss's theorem and rearrange the terms in the previous equation and obtain the equation that you see here, 351, which is the top equation here. So that is now obtained by using Gauss's theorem. So I'm going to highlight it, in which we have a surface term here and a surface term here in replacing the volume terms. Now the last term that we have here in this equation is a special term, which is, we will just pay attention to it because it represents the product of the stress tensor and the deformation gradient tensor, or the deformation rate gradient tensor. And that is sigma ij times dvi by dxj. And this is the strain rate, Eij, which we can express it. The sigma ij is the stress tensor, which is over here. It has the pressure and the viscosity terms that we derived before, and we multiply by the strain rate tensor, Eij. We obtain this equation 354 for the last term. And the first term on the right hand side, which is and here, which is this term here, is minus p times Ejj, is obtained as follows. So minus p times Ejj is dvj, so this is vj with respect to xj, and the dvj by dxj is the rate of change of the volume. So we get 1 over rho d rho by dt, and that replaces the first term on the right hand side. The last two terms on the right hand side, these are associated with the viscosity, so we will lump them together in a function called phi, and phi is 2 mu Ejj squared minus 2/3 mu Ejj all squared. And notice that this is different from Eij squared. This is right here, and this is Ejj all squared. Ejj is a sum of 3 terms because you sum over repeated indices along the diagonal of the tensor. When you reduce this phi, you can show by yourself that it has this expression 357. And then we have now most of the pieces obtained from the Navier-Stokes equation. So from the Navier-Stokes equation, we basically, the idea here is that we get some expression for the rate of viscous dissipation in the medium. Once we get the rate of viscous dissipation, we can substitute it into the total energy conservation equation to derive the component of the energy that is related to the thermal energy by itself. And that's our objective right now. So if we just continue in to the thermal energy equation now to derive it, we are going to define the energy epsilon per unit mass as 2 parts. One part is kinetic, half VI squared, and the other part is C sub V times T, which is the enthalpy, or the internal energy basically at constant volume, C sub V times T. And then we will do a first law of thermodynamics conservation of total energy. So we're going to do it per unit time, so it would be kind of conservation of total power. So power conservation. So let's look at the different terms in the power conservation equation. The rate of change of this internal energy plus the kinetic, this is basically the internal energy, and we added the kinetic to expand the first law. Remember, the first law is the internal energy is the sum of all of the heat you put in and all of the work you do. Now the internal energy, if you have a moving system, then you would have to include the kinetic energy with the internal energy, and therefore you will have the rate of change of that energy over, if you have 1 unit volume, then you have rho times the mass is rho of the unit volume, and you have epsilon per unit mass, so you have rho times epsilon, that's the energy content. You integrate it over the entire volume, so you have the omega integration, and then you take the time rate, the time derivative of this, you will obtain d by dt of integral of rho times epsilon. And that is the rate at which work is done. Now we're going to have to, this is total energy. So the total energy will have to be all of the components that we would consider. And the components we would consider here is, number one, the rate at which the work is done on the boundary by the stress. And that's where we have to get in that from the Navier Stokes equation. And then plus the rate at which the work is done on the fluid inside omega by the body force, the B sub I. And then if we have energy production inside, that would be a positive. So all of these work or energy, whatever is done on the fluid, either work or energy, is positive. And now the negatives will be the rate at which work is conducted across sigma. The energy is conducted across the surface S, and also the rate at which the energy is convected across the surface S. So we have 1, 2, 3 positive and 2 negative. So the first positive is the work done on the boundary, VI sigma ij dsj. The second one is the work done by the body forces. So this is rho VI bi d omega. Force times displacement rate, which is velocity, gives you the work done. And then the third one is Q triple prime dot, which is the energy produced inside the omega. And then the convected and conducted energy pieces. The conducted energy piece is here. We have K times dt by dxj. This is the heat conduction through the surface. This is K times dt by dxj is Q double prime. This is the surface heat flux. And also we have a heat flux that is carried by the moving fluid. If the moving fluid has a convective velocity Vj, and it will convect with it an amount of energy epsilon per unit mass times the amount of mass rho, and that will go across the surface. So these are pieces that we have to do to get a total balance of energy, and we will just proceed. You have the details in the notes, but we just get some ideas here about how to substitute in this equation. First term is the work done on the boundary by the stress. So we have to put in the stress from the previous equation, and that gives us these terms here in the equation that you can see 360 right here. So if you see like 360, it gives you, we substitute for the work done by the stress on the boundary, and that is obtained from, if you look at the expression for the stress, you see equation 351. You will see that we can isolate this term here. This is VI sigma ij dsj, and we just move everything to the left side, and this will give us the rate of work that is done by the stress on the boundary, and that is the equation that we see here in equation 350. So this is now just sigma ij times Vj times Vi. So next, what we want to do is we want to just compute the convected quantities, the conduction through the surface and the convection through the surface of energy. The conducted through the surface is the heat flux, and we use Gauss's theorem to rewrite it in a divergence form. And the divergence form that you have here is simply stated in index notation. That is d by dxj of the q double prime. Q double prime is k dt by dxj. So you have now basically the divergence of a gradient, and the divergence of the gradient, if the k is constant, independent of space, you can take it out, and that will turn out to be a Laplacian of the temperature. Now the next one is the energy that is convected across the boundary, and we substitute for epsilon. It has two terms, the kinetic energy and the internal energy, CV times T, and those are across the surface. And here again we're going to try to use divergence theorem as usual. So here if we look at the continuation of this, then we can combine the equations, the previous equations, and we get the rate of change of rho c sub v times t to be equal to the divergence of k times the gradient of the temperature plus the internal energy that is generated, q double prime, in the volume, and then we have the work done from the mechanical forces that we talked about, the Navier-Stokes equation, and then we have now the convected energy through the boundary. And since this holds for, so this, we're almost there in as far as the equation now, the Navier-Stokes equation is substituted already, and we get an expression. Excuse me. We get an expression now that describes the thermal energy conservation, because we eliminated the mechanical part of the total energy, and we get a thermal energy equation, as you can see here. So I'm going to guide you through the rest of this here. Excuse me. So if we now look at equation 363 and localize it as usual, we get rid of the integrals because it holds for every volume element. Then we have the rate of change of the internal energy, and then the convection of that energy is now equal to the heat flux that is passing through the surface, and is given by the divergence of k times the gradient of t, and then the energy that is generated inside the material could be due to chemical reactions, or could be due to electromagnetic heating, for example. And then the last two terms, these two terms here, are what we have subtracted out from the total energy equation using Navier-Stokes equation multiplied by the velocity. When we did that, we got the work done by the mechanical forces, and that resulted in this residual amount that represents the work done by the pressure on the fluid and the work done by the forces due to turbulence and viscosity. So if we have now, we look at equation 364, we can simplify it a little bit further by using changing the index notation into a vector notation. But before we do that, if you look here at the divergence of, look here, the divergence of V I times CV times T. So we could use the chain rule, and when you use the chain rule with VI as one variable and CV times T, rho CV times T as another variable, then you can use the continuity equation. You get two terms, and then by the continuity equation, one of them drops out, and the result is only one term in here. So if you look at the total internal energy, which is CVT, then we notice that we have rho d by dt operating on it and rho vj d by dxj operating on it, and that is equivalent to rho capital D by dt, and that is the total material derivative operating on capital U, because capital U is equal to C sub V times T. So on the right hand side we have the minus the divergence of Q, and Q is the heat flux. This is the heat generated inside the volume. This is the work done in compressing the fluid, and this is the work done by the viscous forces. So equation 366 is a more complete equation that we could use in our simulations. But in order for us really to use it, we need to know something about the fluid mechanics. So we need to know the velocity field. So at the end of the day, we need to know what the velocity field is. And that means that we have to solve the Navier Stokes equation together with the equation 366 if we have if you have a moving fluid, like in the case of doing continuous casting, for example. However, if we assume now you have an incompressible fluid, the divergence of V is equal to 0, and du, the internal energy increment, is C dt, where C is equal to C sub P equal to C sub V. We don't have phase change of chemical reactions, and therefore we get the final form of the equation in 367. And moreover, if we have now if we assume that the viscous forces are small and negligible, then we will finally now get the equation for thermal energy by itself, which is rho times, you can see here, this is the final form that we have, is that rho times C sub P times the rate of change of the temperature. This is the material derivative of the temperature, equals to minus the divergence of Q plus the internal heat generation inside the material. So this is a diffusion of thermal energy, a thermal diffusion of temperature, basically, through the material with fluid motion that you can have. I'm going to give some examples using finite element, so how you can use these equations within COMSOL, so you understand the different terms and how to use them in practical applications in a few minutes. So let's just continue here and see that now we have, if we have the temperature gradient term dominates, then, and we use Fourier's law, so Fourier's law is given here, then we will find that we have essentially an equation that represents transient heat conduction, and capital D by dt is the material derivative, and on the left hand side you have minus alpha, and alpha is the thermal diffusivity, K over rho C sub P, and the heat that's generated inside the material is scaled by rho times C sub P in the equation. So that is a simpler form that can be used, and in fact we're going to solve it analytically in the class and in several examples. Now that we have done that, I will now make sure that we understand how to use these equations in practice. So what I'll do is in the next lecture is I will present to you the finite element code console and point out the two modules that will be important to use in conjunction with these continuum equations. One module for heat transfer and another module for material or thermal diffusion, and you will use both modules in a variety of applications in material processing. So we're going to stop at this point, and we'll pick up with practical applications in the next lecture.